So welcome everybody to the final first Friday math seminar at Simon's Rock, the final seminar of the semester. So we're very pleased today to welcome Sam Ferguson, who is a former Simon's Rocker. He actually graduated from Simon's Rock in 2010. In 2018, his work on Obamacare, which I believe we're talking about today, was spotlighted by the New York Times film crew and Money Magazine. In 2019, he completed his doctoral dissertation from Courant Institute. He's picked up a few other degrees along the way. Since then, he's begun working as a research mathematician at Metron Incorporated, which is a small firm based in the greater DC area. And he's also an adjunct professor of mathematics at George Mason University. And through all that, he's also found the time to do some private tutoring. So if you want some private tutoring, then shoot him an email, perhaps. So all that said, I'll let you take it away, Sam, and I'll just say it's a great pleasure to welcome you back, and we're all very excited to hear what you've got for us today. Oh, and we'll be speaking on, of course, Obamacare and a fix for the IRS iteration. So welcome, take it away.
Thank you so much, Ken. Thank you for giving me the opportunity to give this talk back at my alma mater, Simon's Rock. And thanks to all of you who chose to take time out of your the tail of your last Friday of classes to join me for this presentation. And so I'm going to try to share my screen. And if there's no technical issues, I will successfully share something. Okay, this looks like progress, and maybe we can enter full screen mode. So does everyone see a slide? If not, there may be a problem. Good. Okay, this is promising. So my talk is called Obamacare and a Fix for the IRS Iteration. And yep, I'm over at this kind of mathematical consulting firm and an adjunct faculty at George Mason. So here's kind of the beginning of the story. Basically, how I learned about this mathematics problem was back in 2018. I had friends from when I did my master's in physics before I went to the PhD program at NYU. And so I wanted to visit them out in the Midwest. I took a flight, and the place where they were going to school didn't have an airport. So I had to get from the airport to the college. And there were no taxis because they were all out of business. So I was forced to modernize myself and request an Uber ride. And being a New Yorker, I had usually used the subway, so I wasn't really familiar with Uber in detail. And I talked to my Uber driver all about his job, my job, taxes, health insurance, all those kinds of things that normal people don't talk to their Uber driver about, right? As a mathematician, I am interested in these things when I encounter them for the first time. And he told me about Obamacare and how he could not calculate how much Obamacare money he should be receiving to help him pay for health insurance, and asked as a mathematician whether I could investigate. Now, if I had, $1 every time someone mixed up a mathematician and an accountant, I would have quite a fortune on my hands. So I was a little skeptical about whether this was a kind of problem that a mathematician would care about. But I did go to some standard math, not math software, tax software, and plug in different things for self-employment income. And occasionally I got strange results that I wasn't sure made sense to me. Sometimes I got lower values or $0 for Obamacare benefits when I wasn't sure that that was correct. And so I wasn't sure if I just didn't understand Obamacare laws or if there was actually a mathematical problem here. So before I go into the mathematics of that, let me maybe briefly remind you of some things regarding Obamacare, also called the Affordable Care Act. So back in the year 2010, the year that I graduated from Simon's Rock, little did I know Congress was passing the Patient Protection and Affordable Care Act, also called Obamacare. And it has so many parts to it, I could not possibly discuss the whole act here in this talk, but I will mention a few facts regarding the act that are perhaps relevant. One is that states which expanded a program called Medicaid to a certain threshold got extra money from the federal government to support that expansion. And another part said that states that don't expand are going to get less money from the federal government. But the Supreme Court struck that down in 2012 as being coercive to the states, the first block on federal expansion of power in perhaps a half century. And so as a result, states kind of can do more or less what they like in terms of Medicaid expansion, which is certainly curious. Another perhaps more practical aspect for everyday people is that online exchanges were set up and such that all insurance on the exchanges met certain minimum standards. So you could know that, okay, if I have a baby or I have certain basic things I want my insurance to cover, no matter what the legalese might say, it will cover certain basic essential things. And so that made it a lot easier to file for certain types of claims. And you can apply for these plans on the online exchanges directly without having to go through a broker. But the sexiest thing for us, of course, is that a new tax credit was created, which has a certain mathematical structure to it. And the purpose of this tax credit is to help households pay the premiums of qualified health insurance. And so basically, in simple mathematical situations, the tax credit gives you an amount of money equal to the whole cost of the plan, except for a certain portion which is considered affordable for you to pay by government definitions. So in other words, by government definitions, the Affordable Care Act makes health insurance affordable for everyone in the United States with income in certain intervals. And if not for the Supreme Court ruling, it might be affordable for perhaps everyone, or at least almost everyone. So it's a pretty elegant mathematical structure that has some machinery behind it. But before I go into that, perhaps I'll show you the little 3-minute video that I think Time Incorporated made, because I think it's a fun introduction to this topic. So let me see if I can find that. Let's see. Okay. Let's see. I hope you can hear this. I'm going to press play. I heard that some people found it hard to find how much money they should get from the government to help them pay for health insurance. So I didn't think it was really an issue. I just thought you could use TurboTax or H&R Block or whatever tax software you like, and it would work. I met an Uber driver who, he seemed pretty smart. He was driving, but he was also going to some kind of college, and he seemed to be pretty good at math, but he couldn't figure out. I just wanted to check, can everyone hear the audio on my computer in this video? Okay, good. How much money the government should give him to help him pay for health insurance. He was not of a high income. And so okay. I'm not sure what happened there. Okay, so I've had some technical issues with this video just now, but I'm going to just return to my presentation rather than wait for that video to sort itself out. Okay, but anyway, there is a video and it's pretty cool. And if you have an opportunity sometime and have never seen it, you might enjoy seeing it. I think it's a good discussion of some of the things that I'm going to talk about in this talk. Okay, so.
Sorry, Sam, do you have a link to the video?
Well, I sent it to Ken some weeks ago, but I don't know where it is at this exact moment. It's also on the last slide of my talk.
Okay, thanks.
Sure. So anyway, there was a cool video. Okay, so basically, this is a kind of image that you can use to get an idea of what kind of money you can get each month from the premium tax credit if your income is a certain percentage of what's called the federal poverty line, which I have not yet introduced, but will introduce in the future. Okay, so this is a preview to get you in the mindset. So I've just, these X and Y axes mean totally different things. Okay, the X axis is your income as a percentage of the federal poverty line, which is a certain number of dollars per year. Okay, so if it's $12,000 and you're at 200%, that means your annual income is $24,000. Okay, so that would be the 200 down on the X axis. The Y axis is number of dollars per month that the premium tax credit is using to pay part of your health insurance costs. And here I've just arbitrarily said that the health insurance total cost is $500 per month. In some parts of the country, that might be considered slightly high, but in other parts, it might be considered a little low. So I think 500 is not a crazy number to use arbitrarily in an example. Okay, so if you were, say, at 200% of the federal poverty line, then the premium tax credit might be paying around $350 or $370 per month. And so you would only be paying maybe $130 per month. Okay, now that still might be a lot of money, but it's a certain percentage of your total income that the government considers affordable for you. You may not agree with the government's definition of affordable, but at least under its definition, it is affordable within an internally consistent manner. Okay, and then you'll notice there's some weird things about this graph. Okay, there's a little discontinuity, a jump downward over somewhere to the left of 150. And this is ultimately created by the Supreme Court ruling in a manner that's not very easy for me to explain. But there is this jump downwards there, and then at 400%, a jump downwards to zero. For some reason, the way that the law works is there's only a subsidy or tax credit if your income is 400% exactly or below. So if it's 400% plus $1, you just get nothing. So be sure to lower that income in some way. Or try to make less money, do something so that you're at 400% or less, or else able to pay the full cost of the insurance. Okay, so now I've introduced this ultimate function that will be arranged. Oh, looks like we have additional cat joining us in the audience today. Excellent. It's always nice to have mathematically sophisticated felines. Okay, so now I'm going to introduce the mathematics of the premium tax credit mechanism by itself. Okay, please keep in mind that this is deterministic stuff. So this is not where the mathematical problem lies, but it is a part of the mathematics as a whole that we want to consider. So how does it work? So the first step is you're going to have some kind of gross income for your household, which I would call I for income, and then certain deductions D that are on the beginning of a classic tax form called the Form 1040 for American citizens and a similar one for permanent residents. So that income minus the deductions give what's called household income. And I'm calling that M because it's sometimes also called modified adjusted gross income. And I don't want to say that again, so I'll just call it M. Okay, so that's easy, provided you know the income, and you always will know that if you have appropriate paperwork. And then the deduction D might take some time because you might have to deduct student loan interest or pre-tax retirement contributions in certain circumstances and so on. But once you know D, you know M. Once you have that, you have a separate thing where you look up what's called the federal poverty line for your household. This is a function of the number of people in your household, primarily. And so it's often, in recent years, about 8,000 plus 4,000 times the number of people. So if it's 2 people, it'll be 8,000 plus 8,000 is 16,000. If it's 1 person, it'll be about 8,000 plus 4,000 is 12,000. If it's 3 people, it's about 8,000 plus 4,000 times 3 is 8,000 plus 12,000 is 20,000, and so on. It's basically a linear function. I've rounded everything to whole multiples of 1,000, and it would actually be about $25,000 for a family of 4 rather than 24,000. But nevertheless, that's a rough idea of how the federal poverty line for a household is calculated. It tends to rise each year, and it is slightly different for residents of Alaska and Hawaii. Now, once you have your household income M and your federal poverty line F, what do? You just divide. You divide the income by the federal poverty line and get a real number. And this is very important. It's an exact value. This is the only place in the US tax code, in federal tax law, where you can't round. So this requires infinite precision. Okay, if it's pi, you know, that's just the way it is. Okay, if it's the square root of 2, well, that's just the way it is. Now that's unlikely, okay, but you don't round, you get an exact number. And if this is anything more than 4, like if it's 4.000001, for example, you get no premium tax credit, no tax benefit. Okay, it has to be exactly 4 or less to get the benefit of the health insurance premium tax credit from Obamacare. So we have this real number, and it's a bona fide real number, no rounding. And now, under normal circumstances, it's in the real interval from 1 to 4. Why? Because if it's greater than 4, you already know you get no money. Okay, if it's less than 1, then either your state gives you Medicaid, which is perhaps better because it's often even cheaper, or you're in one of those states which did not expand Medicaid and you are too poor to get any assistance from the government. And then I guess the government just expects you to die from any illnesses you have or something like that. I don't know. But that's, you know, due to the Supreme Court ruling. So in my home state of South Carolina, for example, you need at least a 1 there to get that eligibility. Otherwise, you get nothing. Okay, so now there's a government-defined function, which is right continuous and generally non-decreasing or increasing, as the case may be, that maps these real numbers to numbers between 0 and 1, which you can think of as percentages. Okay, and you can, that answer is called your applicable figure by the government. And so you can think of it as the percentage of your income that is affordable for you to pay for health insurance according to the government's definition of affordable. And this function is different every year, but by the grace of Congress, it is always right continuous, which is a pretty amazing fact that Congress could accidentally do something that gives a decent mathematical property. Okay, and this is the basis of all my work, is the right continuity. Without at least one assumption, I cannot really do analysis, can I? Okay, so finally, you multiply your household income M by that percentage, and that is the actual number of dollars that the government considers affordable for you to contribute for your health insurance. And that's called your expected contribution. So now you have this amount of money that's affordable for you to pay for health insurance, but what are we missing? We're missing the health insurance, right? We need to actually talk about the health insurance in order to calculate how much the government should pay for it. So that's the last ingredient. So if I take the health insurance you actually purchased, the monthly cost, and multiply by 12, I get the annual cost. And the number for the monthly cost is the total cost, not the amount that you're paying, not the amount that the government's paying, but the sort of full sticker price, okay, that you would see if you saw it on a shelf in a store. Okay, so P is the total cost of all the premiums without any government subsidies for the whole year. But the government can't tell you which insurance plan to buy, okay? So it can't base its calculations on the specific plan you chose. Instead, it has to use a benchmark plan to allocate money to you. This is federal law, and this is because of this illusion that we have a totally free market for everything in the United States. So they can't give you money based on what you purchase, but only based on a benchmark plan. Now, how they chose the benchmark plan seems totally arbitrary to me, but it is something that doesn't depend on which plan you choose. So basically, you need this number, the annual cost of a specific health insurance plan picked by the Affordable Care Act as the second cheapest silver plan. I won't say which one that is, but it's a specific plan. And hence, you can use that to calculate specific dollars that go to you to help you pay for health insurance. And it's not the cheapest, and it's not the most expensive. So it's somewhere in the middle. And that value, its cost, depends only on the county you live in, your age, your smoking habits, and the year in which you purchase it. So anything else is not relevant for determining your health insurance costs, which could be good if you have other health issues like an underlying condition, or bad for you if you're like 110 and not eligible for Medicare. Okay, but that would be very rare. Anyway, just things to know. And now finally, what the government sends you is called the premium tax credit because it's paying for the premiums of health insurance. And that's usually equal to that Q, the whole cost of the benchmark insurance, minus the part that you're expected to be able to affordably contribute. So it's as advertised, the government is paying all the cost except for what's affordable for you, at least for the benchmark plan. Okay, which you may or may not have actually purchased, but there you go. And now there's a few other inequalities that have to be satisfied. The amount the government is sending you is never negative. It's never going to say, oh, you bought health insurance? Send us extra money because we're sending you a negative amount. No, that never happens, luckily. And also, you could say, oh, that money they're sending me is for the plan in the middle, but I'll pick a super cheap plan and then pocket all the extra money that they send me. Yeah. No, it doesn't work like that either. They will never send you more money than the full cost of your insurance. So if they want to send you like, $20,000 and you pick a plan that's $10,000, you don't get to pocket the extra $10,000. They just send you the full cost and that's done. So that's why there's a minimum between the full cost P and the value, and there's a maximum that prevents it from being negative. So that's a formula for the premium tax credit. And what you should be thinking now as a mathematician is, this is boring because there are no mathematical problems in sight. Well, you might be thinking that. I was, okay? I was thinking, hey, I can compute this without any mathematical issues. No theorems are needed. So why can't my driver find his premium tax credit? Can't everyone do these kinds of computations with the calculator? And the answer is that, well, this is true for employees, what I just said, but he is actually self-employed. An Uber driver is an independent contractor or self-employed person. And you might not think that matters. But there's another rule that says, an older rule that Congress did not consult when writing the Affordable Care Act. And this older rule says that for self-employed people, they can subtract the cost that they are paying out of pocket for health insurance from their income before calculating their taxes. Okay, because that's an advantage that employers have that employees do not always have. So as a self-employed person, there are two people. They are their boss and their employee. So they get this employer benefit of subtracting the health insurance costs. Okay. Now that, again, does not sound like a big mathematical problem, does it? So basically, if you have the income I and your deduction D is that out-of-pocket cost for your health insurance as a self-employed person, you take I minus D, get your household income M, and you know all these other numbers because they're sent to you on tax forms, usually, unless your state is dysfunctional. But anyway, it's usually sent to you by your county or your state, and so you compute the premium tax credit, no issue. But there is an issue. There is a severe issue. What is the deduction D for the out-of-pocket cost of his health insurance premiums? Is that actually known to us? So D is not the sticker price of the insurance. It's not. What he pays is the part that the government does not pay. The government pays part, he doesn't pay that part. He pays the rest. Okay, so D should be the total cost minus the part that the government pays, called PTC. So P minus PTC should be the deduction D. So that's what D should be. So that's what I need to tell my Uber driver to do, is just, fill in the total cost minus what the government pays, and that's what you pay. And you deduct that part, and now you can do your taxes. Okay, so how does he find the premium tax credit PTC? Well, he uses that formula from before. But there's a problem, right? That formula, you can write it in terms of D by replacing M with the income I minus the deduction D. And now you see, to find the deduction D, he needs the premium tax credit. But to calculate the premium tax credit correctly, he needs to know the deduction D. But to find the deduction D, he needs his premium tax credit. But to find the premium tax credit, he needs the deduction D. And this is very bad. It's called a circular relationship in the federal tax code. These things are not supposed to exist because you need to know the second half of your taxes to know the first half, but you also need the first half to find the second half. So it's just a mess. And this is why, this is why my Uber driver could not determine how much money the government should send him to pay for his health insurance premiums. Not because he couldn't use a calculator or tax software, but because these two variables mutually depend on each other. You need to know both of them to calculate either of them. Okay, and this is actually a modest but arguably non-trivial mathematical problem, at least for someone, right? So even though this is not an advanced problem in algebraic geometry or a PDE, differential equations, but it's nevertheless arguably non-trivial mathematical problem. Okay, so now as a mathematician, he's finally got me interested. I'm like, okay, maybe there's a little something to this problem. I guess I'll look into it seriously now. So unfortunately, I can't just prove theorems. I have to understand what the rules of this game are. What are the constraints on the solutions that I seek? Because I don't want to find a solution that the IRS rejects. That would be a waste of my time. I mean, if there's a cool theorem, it wouldn't be a waste of my time, but it would be a waste of my Uber driver's time. Okay, so the Internal Revenue Code provides no unambiguous resolution of the circular relationship. This is bad because I like things that are unambiguous when I prove theorems. However, it does provide a constraint, which is a meta rule in the Internal Revenue Code. And this meta rule says that every dollar spent on anything, but in particular, any dollar spent on health insurance premiums, can go into $1 of tax deductions or $1 of tax credits or neither. But it can never, ever yield $1 of both tax credit and tax deduction at the same time. That would result in a negative total cost, which, although beneficial for you, is not the way that the federal government wants to operate. It doesn't want to have a negative cost of health insurance because then everyone will get the negative cost and they might go broke, although they're actually already broke, but that's a separate issue. Anyway, so basically, a certain number of dollars from P can go into the premium tax credit, and a certain number of dollars can go into the deduction. And if the sum of those two is ever bigger than P, then by the pigeonhole principle of mathematics, you would have some dollars that ended up in both, which is violating the no double dipping rule. Therefore, the sum of these two has to be not greater than P. Therefore, it's less than or equal to P. So this is a sketch of how the no double dipping rule leads to this inequality that the sum of the tax credit PTC plus the deduction D has to be less than or equal to the total cost of the insurance P. So this is a constraint. And I don't know, I don't think there's any question, but basically, if you didn't follow that, you can just accept this inequality as given by not God, but the IRS. Okay. Now, here I'm not going to do rigorous mathematics, but think strategy for a moment. What are my goals? My goal is to solve for the deduction D and the tax credit PTC, because these are unknown. And what's the best case scenario? That P has an equality there rather than an inequality, because that means that the credit and deduction are bigger. Okay, so that leads to equation number 1, that P equals the tax credit plus the deduction D. Okay, and then it's also should be in an ideal world that the deduction D, that's the right answer, leads to the premium tax credit, that's the right answer. Because we have an unambiguous procedure for getting the premium tax credit from the deduction. In a perfect world, that would lead to a second equation that the premium tax credit is equal to the value you compute from D using that formula from before, which is just a formula involving D and doesn't have PTC inside of it. So we have 2 equations in 2 unknowns, equations 1 and 2 in the unknowns called PTC and D. And now I ask you as mathematicians, how should we solve for D and PTC when we have 2 equations in 2 unknowns? If you really feel strongly, you should unmute yourself and tell me how you think we should solve for 2 variables when we have 2 unknowns and 2 equations. What was that? I think someone said, gee, if we have two equations and two unknowns, we might try solving this using algebra or even linear algebra, right? Well, that's not what the IRS said. The IRS said, oh, we should perform a fixed point iteration and have an infinite sequence of approximations of D and PTC, which in the limit, as n goes to infinity, converge to the correct values of D and PTC. So this is one of the most infamous revenue procedures in federal history, right? So this is revenue procedure, the infamous revenue procedure 2014-41. The IRS asked all self-employed taxpayers to use these two equations to perform a fixed point iteration by which suitable values of PTC and D are to be determined. And in the interest of honesty, I wish to give you a brief idea of what this involves. As mathematicians, I think you can appreciate what this involves in a way that the average taxpayer may not. So I will briefly recall that a point AB in two-dimensional Euclidean space is called fixed by a function of two variables with a two-variable output if the input AB equals the output AB. And our two equations above can be rewritten as a single equation between 2 points in Euclidean space. Okay, so PTCD equals this other thing, PTC of D as a function, and P minus PTC. And so in other words, our two equations are solved exactly when the point with x coordinate PTC and y coordinate D is a fixed point of this function. So we've recast the original problem, which could have been solved perhaps by algebra, perhaps. I didn't try, but perhaps. And we've replaced it with a fixed point problem. If we just find a point where the input equals the output for this function, we've solved it that way. So now if G is a continuous function of two variables, and we start with a reasonable guess, x1, y1, we can define an infinite sequence of points in two-dimensional Euclidean space by just taking the first point, plugging it into G, getting a second point. Plug that point into G, get a third point. Plug that point into G, get a fourth point, and so on. We end up with an infinite sequence. And if the sequence has a limit as n goes to infinity and G is continuous, then it follows that this point is a fixed point. And so the IRS equations are solved, and we have found the premium tax rate and deduction D for our poor Uber driver or any other self-employed person in this country eligible for Obamacare. Okay, let's take a deep breath. So.
Well, can I ask a question? Sorry to interrupt.
No, please. This is a perfect opportunity to ask a question.
Right. I feel like I interrupted your deep breath though. Like, did anyone study the dynamics of this iteration? Like, I don't see why the fixed point that you're actually looking for is sort of attractive in this sense. Maybe, you know, like it's a fixed point that you're kind of circling around, you know, like your PTC thing has these sort of bounds. Maybe you sort of run into the boundary of your region. Like, it seems, you know, under ideal circumstances, there's one attractive fixed point and you kind of circle in on it. But, you know, unless you have, you know, stronger properties on the iteration, it seems very optimistic to believe that this is going to converge to your one ideal, you know, tax form number.
Okay, so although I cannot necessarily answer your question about what the IRS did and did not do with this iteration, I can say that my thoughts in 2018 were identical to your thoughts now. So I was unsure whether the limit would always be this correct value and whether the iterates might sometimes dance around some boundary region or fail to converge or converge to the wrong or whatever. Yes. So this made me more interested in this problem. And I will say that this procedure, the author is listed at the end of this document, and he's a lawyer. I don't know if he's trained to analyze the dynamics of these fixed point iterations. In fact, I sort of suspect he never analyzed them, but I don't really know for sure. All I know is that after he wrote this, he left and joined a big law firm in New York City and declined to ever answer questions on this again, to my knowledge. So we don't really know what he did or didn't do. I suspect he watched A Beautiful Mind, learned about fixed points, and decided that everything should be solved by fixed points. But that's a personal prejudice I have. I don't really know for sure what he did or didn't do. Anyway, perhaps we can put these questions on hold for a brief moment and ask, do we have to perform infinitely many iterations to finish this? Because if so, this is an onerous burden on federal taxpayers to take an infinite amount of time to fill out their federal tax form each year. And luckily, the IRS produced a hundreds of pages document called Publication 974. And remember, that revenue procedure was just a few pages written by a lawyer that said all federal taxpayers should do this. But it didn't explain in detail how to do it step by step with only a calculator and no algebra by hand, like revenue procedures are supposed to do. That's why they produced this book. This book goes step by step where you can fill out long forms that end up producing each iterate of the procedure just using a calculator and moving things from one line to the next line. Okay, so basically the IRS produces this giant document which answers all your questions about the how, but not necessarily the why and whether it works. Okay, and it says to continue until the changes in the X and Y coordinates, the absolute value of the changes at each iteration are less than $1. Then it turns out, because these sequences turn out to always be oscillatory due to the choice of initial condition, this is equivalent to the Cauchy condition for convergence in real analysis, which some of you may know, with epsilon equal to $1, and with the infinity norm chosen on two-dimensional Euclidean space. So basically, this is a mathematically correct way for defining convergence with a cutoff in error. Okay, so the convergence is unambiguous. It either converges or it doesn't. And if you are converging, after a finite number of steps, you'll be less than $1 away from the answer, and you can stop and round and get your answer and be done. Okay, so the guesses are $0 for your Obamacare credit. What a convenient initial condition. And the deduction equal to the full cost of the insurance. And then you get the sequence of iterates. And if the limits exist for both of these in the IRS sense, you can actually use the left continuity of the premium tax credit, which I mentioned earlier. It's right continuity for one thing, and then we get it in terms of D, it's left continuity because D has a minus in front of it. And in that case, you can show it gives the correct values. It is something I've proved for myself. I'm assuming both limits exist, and I'm assuming the left continuity. Okay, but given all those things, you can prove that this does work to find the correct answer solving the problem. So it can never converge to the wrong value. But does it converge? And my answer was no. So I just took a random income value from a friend of mine in South Carolina, which is the state that I'm originally from. And due to the Supreme Court discontinuity, I believe, the iterates for their premium tax credit do not converge. They oscillate up and down ad infinitum between two values which are more than $1 apart. And as a result, there's no solution to this problem provided by the IRS procedure. You can see that the initial guess is 0. I have the x-axis being the index of the sequence. So at n equals 1, I start with a guess of 0, then it jumps up to something around 7,000, then it jumps down, up, down, and never really settles down. And here I've just zoomed in, starting from n equals 2, you can see that there's a difference of more than $150 between the upper number that it bounces around, which is called the lim sup of the sequence, and the lower number that it's bouncing around at, which is called the lim inf of the sequence. Okay, and in general, IRS guidance gives you at most the lim inf of the sequence, which is that lower number around like 6,700, not the upper number 6,850. And this might be less than the correct value for you, which the IRS procedures do not tell you how to determine in this case. But it does say, the IRS procedure does say, if after infinitely many iterations, it never gets within $1, then do not use this procedure. So after infinitely many iterations, it does this, where it oscillates forever, then don't use it, but they do not provide an alternative procedure. They just say, in this case, any procedure which satisfies all federal laws is appropriate, but we do not offer any alternative procedure. Okay, so this does not, so basically we found this procedure does not always work. And here I've graphed all the numerically computed lim infs and lim sups. Okay, so the lim infs are in orange, the lim sups are in blue. And you see, basically, there's some details I'm skipping, like the x-axis represents I, the gross income, not M, the household income after deductions. That's why it's goes beyond 4 here. Okay, and I've picked arbitrarily a specific cost of the insurance to be, say, $500 a month. But the point is that you can see that the lim inf and lim sup disagree near the 2 places that correspond to the 2 discontinuities. That's the message I want to send, is that when you create discontinuous laws and then require the computation of tax quantities to depend on theorems which require continuity of those laws, you run into problems due to the lack of continuity. So the hypotheses of the theorems used in federal laws are essential, and without them, you get ambiguous federal laws, which require the assistance of outside people, perhaps, such as myself. Okay, so here just I've zoomed in on these numerically computed lim infs and lim sups near the Supreme Court discontinuity. Those little bumps up and down have to do with idiosyncrasies in the 3 different rounding procedures employed in the dollar number computed. But the little tiny differences between blue and orange on the right don't matter so much as the big jump between the blue and the orange around that 1.66 x value. Okay, so that's bad. And this is even worse. Near 400% of the federal poverty line, no information is known about what the correct value should be. The lim inf is 0, so all these people have been receiving no money for Obamacare for years, since 2014, when this procedure was introduced. Okay, and the upper number is obviously too high. It's bigger than numbers to the left of it. So nothing is known in that region. So naturally, I proposed a method to solve this problem and had it soundly rejected by the people who wrote Obamacare, some of whom were working at the NYU Law School at the time. But before I get to what worked, I will give you a brief idea of what happened. What happened was the IRS procedures can fail due to discontinuities. And in fact, the 2 equations of 2 unknowns can fail to have any solutions due to discontinuities in PTC of D and a jump. So in the case where the equations have no solutions, the iteration always diverges, and the taxpayer receives at most PTC of the lim inf. And what I proposed was to just take a 2-variable optimization of the tax benefit. And then the solution to that is best for the taxpayer. And the constraints are due to the no double dipping rule and the fact that the premium tax credit won't be larger than the amount computed using the law. And the tax benefit is the credit plus the amount of money you saved on taxes due to the deduction. And the tax attorneys at NYU, some of whom were part of the team that wrote the Affordable Care Act, explained this was not suitable because the variable PTC is not a variable at all. It must be exactly equal to the amount computed by the function PTC of D. So what I thought was a 2-variable problem is really a 1-variable problem, which made my life so much easier. Basically, PTC has to exactly equal the value from that function I mentioned earlier when you plug in D. So the only free variable is D. Okay, I just wanted to emphasize that. So if it's 1 variable, then I'm solving a 1-variable problem. And it turns out that the thing I'm maximizing is monotone increasing. as D increases, your after deduction income decreases, which means your subsidy, the amount of money the government is sending you, is increasing. So the bigger the D, the bigger the PTC. It's fantastic. And also, since our tax system is still progressive, as D increases, I minus D decreases. So the tax decreases, which means minus the tax increases. Therefore, the whole thing is just an increasing function. So the maximum occurs at the largest value of D that you can plug in, for which the constraints are solved. So all I have to find is the maximum D such that the no double dipping rule is true. And now this problem is much easier than the problem at the beginning. And I proposed a second proposal. I said, try all possible values of D that are between 0 and the full value of the insurance. The largest for which the inequality is true yields the greatest tax benefit. And this is a true statement, which was rejected by the IRS because they said only new procedures that are admitted to IRS guidance must be such that they can be done by hand in a reasonable amount of time. Now think of the irony here. Can their old procedures be done in a reasonable amount of time? Not if you have to go through infinitely many iterates to prove that you're always bigger than or equal to epsilon apart between your lim sup and your lim inf. And in that case, you don't use that procedure anyway. But basically, I was very frustrated that they were applying higher standards to me than they place on themselves. But okay, they rejected me because they claimed I couldn't try every possible value in a reasonable amount of time by hand. And that's true. So I needed to develop an alternative procedure, which could be done by hand in a reasonable amount of time. And that's where I went to a classic proof of the intermediate value theorem, where you compute a midpoint, or no, not a midpoint, but a value of x, such that when you plug it into a function, you get a specific value of y. And you compute it by looking at the midpoint of the interval and testing to see if it's too big or too small. If it's too big, you look at the left half of the interval. If it's too small, you look at the right half of the interval. And now your search space has been reduced to half the length. Then you repeat it, test the midpoint of the new interval. It'll be too big or too small compared to that value of k you seek. You can use that to look and find that the search space is again reduced in size by a factor of 1/2. And now, if you do this infinitely many times, there's one point C in all of the intervals. The left and right endpoints of these intervals converge to that point. And because the function is continuous, you can prove that f of C equals that value k, and you're done. But what's important here is that after a finite number of steps, the length of that interval has been halved so many times that its length is less than 1. Or if it was in dollars, the length is less than $1. And at that point, you would stop the procedure because you only care about whole dollar amounts in your final tax return for the IRS, possibly pennies if you're very meticulous. So basically, in a reasonable amount of time, my interval length is small enough that I can stop the procedure even if I haven't found the unique real number that's the answer. So that's what so basically the IRS agreed that bisection or halving of intervals can be done in a reasonable amount of time. And now adopting this method, I saw the largest value of D in the interval such that the function G, which is equal to PTC of D plus D, satisfies G less than or equal to P, which is the same as the no double dipping rule. So in the non-trivial case where PTC of the right endpoint is greater than 0, we have a case similar to the intermediate value theorem. The only difference is our function is only one-sided continuous, but it's monotone. So after repeatedly having the intervals, there's a unique number D infinity, I call it, which is in all of the intervals after you have them and apply the test. But by the grace of Congress, the function is left continuous. So creeping up on D infinity from the left endpoints and using the left continuity proves that the inequality I seek, G of D infinity less than or equal to P, is true for the limiting value. And as G is strictly increasing, there is no larger suitable value of D in my interval. Therefore, I've found the unique number, D infinity, which is the optimal one for my taxpayer. And they can compute it in a reasonable amount of time by having until the length of the interval is less than $1 or a penny. So using this procedure, my driver claims he found an appropriate value of D and got a larger premium tax credit than offered by any IRS guidance or tax software. Hundreds or thousands of dollars more, I don't remember exactly. He filed his tax return and got his deposit from the Treasury in his bank account. And many people have done this since then after this appeared in Money Magazine and other places like that. So here are my references. The first is due to a paper I have on Archive, the most recent version. The second is the publication 974 with all the details of the original procedure. The third is just that Money Magazine article, and it is a video and article now in different places online. And then there's I've directed an undergraduate at City Tech in Brooklyn to make a calculator that performs these calculations. And I'm not sure if it's perfect yet, but it's close to being right, except for maybe some rounding issues. So it's 5 o'clock, and we've taken an hour. Thank you so much for coming. If you have any questions, I will stick around after the talk. I hope you enjoyed it.
Yeah, thanks so much, Sam. Appreciate it. So, round of applause.
Thank you.
Yeah. So, are there any questions for the speaker? Well, yeah. If there's no questions, and since it's 5 p.m. on Friday, maybe we'll call it quits. But yeah, thanks again. That was a
thanks,
wonderful talk.
Cool. Well, so I guess you ended up like contacting this Uber driver, or going, getting the Uber drivers in contact information and going back and forth about this for a while.
And the IRS only accepted my work recently when it was accepted in an academic journal for publication. But before, they accepted it informally on an informal basis from the moment that I did it. But it was only sort of formally admitted when this was accepted for publication. So that's when they came to agree with me as an institution. But all the tax returns that use this method have been accepted the whole time, because all they do is when they check tax returns, they just check that the no double dipping rule is true. And if it's true for that tax return, they accept it and give you the money. So everybody who uses this procedure has always received all the money from it. It's just a question of, will the IRS actually write another 100-page publication explaining to people how to use bisection or not? That I don't know.
Well, if they ask you, would you write it, or would you say no, thank you?
Oh, I would say no, thank you, because you have to turn everything into a sequence of instructions like add line 1 to line 3, multiply line 4 by 0.05. And honestly, Ken, I do have better things to do with my life than write those things.
Don't tell that to the tax attorneys. But
Don't worry, it's a secret from them. But as a mathematician, I have other priorities for my life.
All right. Well, yeah, much appreciated. Thanks again. Another round of applause. Really appreciate the talk, and it's great to see you.
Great. Thank you all for attending.